All right, ladies and gents, I'm going to give you a brief intro into chi-squared. I just want you to know that I'm also going to share with you the Bosman video that goes over chi-square. I think with chi-square, if you haven't had any experience in a math class, it's really good to hear multiple people explain it in slightly different ways. I think it, number one, helps it sink in, and number two, I think sometimes it just takes that slightly different touch onto explaining it to help you kind of take it all in and see it from different perspectives. So I would really encourage you to also watch the Bosman video. If you still feel a little fuzzy, maybe go out there, look for other videos and resources, and know that we are going to come together to do the M&M lab on Friday, so that will also help. So we're going to talk about chi-square, and we're going to walk through an example together, and then I'll also set the stage for the lab. So let's take a situation where there's two people side by side, and they're going to toss a coin 20 times. What are the possible outcomes of that? So I think it's pretty obvious that each person can get either a heads or a tails, and then you would get a combination. So you could get one head, one tail, or one tail, one head, two heads, two tails. So there's a couple different combinations that are possible. And if you think about, what would I predict what would happen, right? You're forming a hypothesis about that prediction, what you think is most likely to happen. But then we have to look at what actually happens and compare it back to our prediction to see, was our prediction accurate? So this is where we need a null hypothesis. A null hypothesis is different than the hypothesis that you're used to writing. So normally in science, you write a hypothesis that in statistics we would term the alternative hypothesis. And that's saying that you think there's a relationship between these two particular items, events, whatever it might be, used to independent and dependent variable. If I do this, then I think this is going to happen. So there's a relationship between those. However, the null hypothesis states that there's not going to be any statistically significant difference between these two groups or these two situations. Anything that is different between them could be explained by random chance. So an alternative suggests there's a difference, a null suggests there really shouldn't be a difference. And no statistically significant difference is really important because we're going to use math to show that there is or is not a relationship. So that's what makes the null hypothesis so important, because it's a lot easier to prove no relationship than it is to prove a relationship. Because if you think about it, in an experiment, you could say you think this one thing is going to cause this other thing to happen, but we know that experiments and situations are really hard to create a perfect scenario, to remove all the extra factors from the outside and control everything except your independent variable. So that's why a null hypothesis is a lot easier to prove statistically. Here are a couple examples. So an alternative hypothesis that you might be used to writing or seeing would be something like, if you take large doses of vitamin C when you have a cold, then the length of the illness is going to decrease. So that hypothesis is suggesting there's a relationship between taking extra vitamin C and the length of your cold. But a null hypothesis would say that if you take large doses of vitamin C, then the time you are sick is not going to show any statistically significant change compared to those not taking it. So it's saying, again, there's not going to be any relationship. And this no statistically significant change, that is critical. We need to make sure that that's always in there for a null hypothesis, because we want to acknowledge that we're going to be using data to support what we're going to say. Another example here is if sexual selection favors bigger feet in male chickens, then the average foot size in the male should be larger than the average in the female. So if we're thinking about evolution and sexual selection, if females are more attracted to males with big feet, then the size of feet in males should be larger than females. And then again, that null hypothesis would say that no, there shouldn't be any statistically significant difference between the foot size of male and females. So for our coin toss, we can think about flipping the coin. And what we're going to do is we're going to analyze the ratio of heads to tails. So how many heads versus tails do we get? Well, we all can pretty much assume there should be a 50-50 chance. So if I toss a coin 100 times, I should get heads 50 times and tails 50 times. Just like when we're using our Punnett square to determine mathematically what the chances are of a child having a certain trait. So when we flip that coin, the ratio of heads to tails will show no statistically significant difference between observed, what we actually get, and expected values. Expected values being our ratio, our 50-50, what we expect to get, if not influenced by other factors. So I kind of just added that in as a reminder that we're assuming that nothing else is going to be at work here except our flip, our natural chance of getting heads or tails. We're assuming the coins are equally balanced. We're assuming that the way we're tossing it is the same every single time. Those could be the influence by other factors that we're acknowledging, you know, this will work if those other factors aren't. All right, the chi-square formula. So first of all, like any other math we've done all year, this formula is on the AP formula sheet, so it's not something that you have to remember. The symbol for chi-square is the x squared, and we're going to calculate that by taking, again, if you do not remember, this is the sum symbol. So we're going to add up each event. We're going to sum them. Each event is calculated taking the observed outcome minus the expected outcome, squaring that, hence chi-squared, and dividing by the expected. And we're going to do that for each scenario or situation in the experiment, and we're going to add them together. And I'm going to walk you through the coin toss example. Okay, so here's my data table that I would set up if I was actually doing this coin toss. So here are my possible outcomes. I could have a head and a head. Each person could flip heads. Each person could flip tails. Or we're treating head, tail, or tail, head equally. So we're assuming that whether it's the first person gets the head or the second, it doesn't really matter. It's the same outcome. If we're thinking about this genetically, these would be our heterozygous individuals. So I just filled in some data that I got. So this is the data that I would get by actually doing the experiment. And now we have to ask ourselves, if we assume that 50-50 ratio, what is my expected outcome for each of these? So my expected outcome, and we can use our multiplication rule here. So if I've got a 50% chance and a 50% chance, that's going to give me a quarter of a percent chance to get both scenarios. I would then figure, well, I flipped the coin 20 times, so a quarter of 20 is 5. I use the same basic principle here, but again, I've got two ways to do it. So I've got a quarter plus rule of addition plus another quarter. So I've got a half, so that would be 10 out of 20. And then again, just like the heads-head situation, I would have 5 for my tail-tail outcome. Now I really broke this down, and I think when you're first doing chi-square, sometimes it's good to break this down into very small steps. But no, once you get comfortable, then you maybe could just go ahead and do the whole calculation, which I don't have here till the end. But I'm just going to walk through step by step. So I take observed minus expected. It's okay if you get negative numbers, because remember, you're going to square this, so that will get rid of the negative. These are my numbers once I take my observed minus expected outcome and square it. And then I'm going to go ahead and do the last step. I'm going to take each of those numbers and divide by the expected value. And then now to actually get my chi-squared, remember I have to sum them. So I'm going to add those three numbers together and I get 9. Now we've got this extra item down here called degree of freedom. So I'm going to tell you what the degree of freedom is for this, and then I'm going to go into explaining it. So the degree of freedom for this would be 2. And I'm sure you're like, well, why is it 2? So let me explain degree of freedom. Degree of freedom is taking the number of possible outcomes. So in this case, we had 3 possible outcomes on our table, and we just subtract 1. That's going to help us use a chi-square distribution table to determine what does this 9 mean. So we got this chi-squared value of 9, but what does that tell us about our null hypothesis? Until we use this table to help us figure out what that means, this number is just kind of a random number that doesn't mean anything to us. So this is the chi-squared distribution table. Again, just like the equation, this table, or it's actually a smaller version of this table, will be on the equation sheet. So again, don't worry about remembering any of this, but you're going to have to know how to use it. So let me walk through that a little bit. I'll take you through the parts. So the degree of freedom is over here on the left. We know from our trial run, our degree of freedom was 2, so we're going to be focusing on this row. Then we have this P up here. So this top row is what we call a P value, or a critical value. That is a percentage of the time you would expect to see similar data due to chance. So what we have to do is decide what is our chance setting for this particular activity. So in this particular activity, and actually in almost every single case, whenever you calculate this, you're going to use the p-value of 0.05. What does that p-value mean? That p-value means that you are 95% sure that any small differences between the observed and expected values can be explained by chance, not some other factor. And generally, 95% sure or 5% uncertainty is accepted in most statistical tests. Sometimes people will want a higher degree of certainty. For instance, maybe 99% sure. But as a general rule, unless told otherwise, use the 0.05. Okay, so we're going to take again that p-value and our degree of freedom, and we are going to line this up on the table. So I went ahead and put a box around the row that we want. We want a degree of freedom of 2, and we want to trace this over to our p-value of 0.05. So the number that we get is 5.991. So that is our critical value. So what we need to know is if our number is above that critical value, we are going to reject the null hypothesis. And in this case, our number was 9, so we were above that critical value. If our number was below that critical value, or right on it, if you had 5.9, we would accept the null hypothesis. We would be 95% sure the small differences between observed and expected could be explained by chance. Another way I like to explain kind of thinking about this critical value situation is to think of it as a drug trial. If you were going to try a new drug, you know, we want to be at least 95% sure that we're not going to have like any weird side effects. And I know a lot of people argue, well, it might depend on what the side effects are and what the symptoms are that the drug is trying to treat. And I totally get that. But just think about it kind of in that circumstance. We're saying any small change in your health could be explained by chance and not the drug, based on the data that we've gotten. So we're 95% sure that you're going to be okay, that this drug's going to do what we say it's going to do. And actually, in a lot of drug trials, we're going to want a higher value than that. That's when we might look at this like 99% sure. But that's just another way to kind of think about what this p-value and critical value means. So kind of using that experience, again, we're going to be doing the M&M lab on Friday. So remember I asked you to get some size bag of M&Ms. So Mars Candy actually used to publish the ratio of each color M&M in their bags, but a lot of science teachers, yay us, use this situation to do chi-square. And I'll warn you now, like spoiler alert, we found out that their supposed ratios didn't really work out per statistical testing. very often. So they actually don't publish them anymore, but we're going to go off of the old numbers and we'll just kind of enjoy it and see what happens. So we're going to use chi-square to test the accuracy of their claims. One thing I'm going to ask you to do before we get back together on Friday is to come up with a null hypothesis for the test. Go back, maybe look at my examples, use them as a template to try to help you write your null hypothesis. Have that ready. And again, there'll be a worksheet for you to use to help you out. And then I'm going to ask that you go ahead and count the number of different colors in whatever size bag you took or picked or got. So just FYI, if you got like a really big bag, I would definitely recruit some family members to help you count maybe Thursday night. Your M&Ms and like how many of each color you have, and then you guys can go ahead and eat them. You don't physically need the M&Ms with you during the lab. We just need to know the counts. So go ahead and record that on your lab sheet and just have, again, your null hypothesis written and your numbers ready to go. And then we will work together to kind of work through the math, talk about the null hypothesis that you wrote, and I'll give you some feedback. And then we'll take a look at the outcome and discuss it. If you have any questions, feel free to drop me a note on Google Classroom. Otherwise, we will see you all on Friday.